Okay, so last time we talked about the periodic table, and we sort of left off with why the periodic table is organized the way that it is. And that's because elements that live within a certain column have the same sort of chemical behavior. And we don't even really know what that means yet. We're going to sort of see that over and over again throughout the course. Actually, the first intro into that will be what we talk about today with the type of charges that these ions form. Turns out that all elements that live in the same column, they all adopt the same charges when they form ions. Okay? Before we go through that, we're going to need to learn how to cut up this periodic table in one additional way here. Okay? So if we take our periodic table and we make this little staircase over here on the right-hand side, where at boron we start going down, then over, then down, then over. We're going to cut up this periodic table into these two chunks here. Okay? Everything that lives on the left-hand side of this staircase, all right, and all this crap down here as well that we don't really talk about much in this course. These are the metals. Okay, so some of these we've heard about and it makes sense. We consider them to be metals, copper and iron. Other ones we haven't really heard of before, niobium. All right, but all these that live to the left-hand side of our staircase, these are our metals. Okay, everything that lives on the right-hand side of the staircase, these are all considered to be non-metals. All right, and then the elements that are actually touching the staircase, let me sort of complete this a little bit. These are elements that have properties that really are kind of in between the two. Sometimes it's more convenient to think of them as metals. Other times it's more convenient to think of them as nonmetals. We kind of put them in this gray area here, which we call metalloids. Okay? Now, there's two important exceptions to this little cutting it up by the staircase rule. One of them, and by far the most important one, is hydrogen. Notice I haven't colored hydrogen over here. Hydrogen, despite living on the left-hand side of the periodic table, is still very much a non-metal. All right, so everybody to the right-hand side of the staircase is a non-metal. Hydrogen's kind of living in the wrong place here. It's on the left-hand side, but it is still very much considered a non-metal. All right, and then the other oddball here is aluminum. Aluminum is also considered to be a metal. Good news is that kind of checks out with what we know about aluminum and aluminum cans, right? We already sort of have this intuitive sense of aluminum being a metal. And even though it's touching the staircase here, we consider it to be a metal instead of a metalloid. Okay? So this is going to be really important because now we're going to start talking about ions. Remember that ions are atoms that have a net charge associated with them. Okay? And depending on whether you're a metal or a non-metal, you sort of behave differently when you form ions. Metals are terrible at holding on to their electrons. They can lose their electrons really easily. So that means that they form positively charged ions. Okay? Nonmetals, on the other hand, are very good at holding on to their electrons. They have a really strong affinity for electrons. In fact, they're really good at pulling electrons off of other atoms. So they will gain electrons to form negatively charged ions. Okay? Our metalloids we're going to kind of gloss over for right now. They're not very commonly formed ions. Okay? So the elements that tend to form ions are either metals, which form positively charged ions, or nonmetals that form negatively charged ions. All right? And we have a fancy terminology for these positively charged versus negatively charged ions. We're going to be throwing around these terminology a lot, so we want to get comfortable with it. Positively charged ions are what are called cations, whereas negatively charged ions are called anions. Okay? Now, these are really easy to mix up here, cation and anion, and sometimes, if you can remember just the stupidest little phrase, it'll help it stick in your mind. All right? And so for that, we have that cations are positive because cats have paws. Cations are positive. Super stupid. You'll never forget it. All right? So anyways, we're going to be referring to this terminology a lot. Or again, cations is anything that forms a positively charged ion. And again, those are metals. Or anions are negatively charged ions. And again, that lives on the other side of the staircase, are nonmetals. Okay? So it turns out that just by looking at the periodic table, we can figure out what charge an ion will form. Okay, so let me get rid of all these markings here. All right, if you remember last class, I was like, oh, this particular element, we did a sodium atom. And I said that sodium atom will form a sodium ion with a +1 charge. And I was like, look, you're just going to trust me on this for right now. Okay? It turns out that all elements that live in this same column with sodium, this first column here, all of those metals form ions with a +1 charge. So everybody that lives in that column there, and remember we had a special name for it, these are our alkali metals, all of our alkali metals form ions with a +1 charge. Okay, so just by looking at the periodic table, I know that rubidium also forms an ion with a positive charge. Never heard of rubidium in my life. Doesn't matter. I know based on where it lives on the periodic table, the type of ion that it forms. Okay? Moving over, everybody that lives in the next column, these all form ions with a +2 charge. Okay, this middle block right here, we're going to skip over for right now. What do we call that middle block? These are the transition metals. It turns out that for transition metals, it's a little bit more tricky. So we'll talk about them here in a bit, all right? We're going to kind of kick the can down the road on the transition metals. Okay? If we jump to the other side of our periodic table, all the way over here, these elements in this last column here, what was their name? Those are the noble gases. They don't form any compounds. They don't like to form bonds with any other atoms. They also don't form ions. They will not gain electrons. They will not lose electrons. They're perfectly happy the way that they are. So they will not form ions with any sort of a charge. Okay? If we move one column over to our halogens, again, these are nonmetals. They're good at accepting electrons. These will all form ions with a -1 charge. Can we see a pattern here? What do we think about oxygen and sulfur and selenium? -2. And we move over one more. These all form ions with a -3 charge. Okay? So by looking at the periodic table, remember we said that elements are grouped together in these columns because elements in a particular column behave the same. And we said we don't even really know what that means. Well, here's our first behavior that we're talking about here in terms of the type of ions that those elements form. Okay? Everybody that lives in the first column, +1, second column, +2. If we jump over and start counting backwards here, our halogens are -1, oxygen's -2, nitrogen's -3. Okay? All right, so let me just sort of give you the punchline of today's lecture, and then we can work from there. Okay? Based on where these two elements live on the periodic table, sodium and chlorine. I know that sodium will form an ion with what type of charge? +1, and chlorine will form an ion with what type of charge? -1. So we're going to mine our periodic table for this information right here. Then we're going to turn this into the formula for the compound that these two form, NaCl, and we're going to learn how to name it. This would be sodium chloride. All right, so that's the punchline of today. This is what we're going to learn how to do. Get these ions, put them together, and name these ionic compounds that are formed. Okay? All right. Cool. So we're going to break this down into steps here. You all wouldn't know how to do this already, right? Again, this is what we're learning to do today. Okay, so first off, let's learn about how to name our ions. Okay? So we're going to start off with the cations. The cations are the easiest one. Okay, but we got to break these into two different categories here. The first one is what we call type 1 cations. These are the ones that we've discussed already that we can determine their charge just by looking at the periodic table. So again, we're going to save these transition metals here for later. All right? So type 1 means that we know the charge by looking at the periodic table. Okay, so let's just grab a few examples here. We already said Na+1. All right, let's grab this SR business. We have no idea what strontium is, but again, we can apply the same rule here. Based on where strontium lives on the periodic table, what's going to be the charge of the ion that it forms? +2. Okay, so what do we call sodium when it forms this ion here? This is simply a sodium ion, or a strontium ion. Literally just the element name that you pluck off of that periodic table. All right? Nothing crazy. We didn't do anything complicated to it. It's just the element name plus that word ion. That's how we name our type 1 metals, our type 1 ions. All right, so again, there are these metals here that form our type 1 ions. Notice I'm skipping hydrogen because it's not a metal, it's a nonmetal. All right, there are 3 exceptions that we just got to know. They live over towards that transition metal block. And that is aluminum. They form a little diagonal here. Aluminum, zinc, and silver. These are also considered to be type 1 ions in the fact that they only ever form one type of charge. All aluminum ions have the same charge. All zinc ions have the same charge. All right, so these ones we just got to know here. Okay, and it turns out they all sit in this little diagonal and they go 3, 2, 1. So aluminum's +3, zinc's +2, silver's +1. All right. So again, let's just put them down here explicitly. Aluminum, this would be the aluminum ion. Zinc, zinc forms an ion with a +2 charge. And finally, silver. Silver forms an ion with a +1 charge. All right, so for our cations, all we do is take the element name from the periodic table and plug that word ion onto the end. Okay? And the reason why we get to just name them so simply is that we automatically know their charge just based on the element, because all strontium ions have a +2 charge. All sodium ions have a +1 charge. All right? Our other type of ion here, these transition metals, all right, as well as our metals that live underneath the staircase here, the Harry Potter elements of the periodic table. These are what are called type 2 ions. And the shtick about the type 2 versus type 1 is type 2 ions can exist with multiple charges. So if we zoom in, for example, iron. Out there in nature, you will find iron ions with a +2 charge, but there are also iron ions that have a +1 charge. All right, you can't tell just by looking at the periodic table what the charge of those ions are. So because of that, with type 2 ions, we build the charge into the name. All right, so now we're going to move on to type 2 cations. Oops. So these are where we don't know the charge, just by looking at the table. So because of that, we're going to build it into the name. All right, so what do I mean by that? I said that iron exists as both the iron +2 and the iron +3 ion. If we're going to name these, we need to distinguish between who it is that we're talking about. So we would call this the iron, in parentheses, using Roman numerals 2 ion. This one would be the iron 3 ion. Okay, so I don't know the charge just by looking at the periodic table. So when we name these ions, we're going to build that charge into the name. Okay, so let's just do another one. Everybody take a second and name these ions for me. Bless you. All right, and at first it's going to be a bit of a word search here because y'all aren't familiar with the periodic table, but again, these things you'll sort of see over and over again, right? At this point, we maybe already have a sense of where sodium lives because we've talked about it so many times. That's just going to be the name of the game of getting comfortable with the periodic table. All right, so first we got to hunt down what the heck Cr is. That's chromium. Since chromium is a type 2 ion, I have to put that charge into its name. So this is the chromium 1 ion. V, pretty cool sounding one, vanadium. Since it's a type 2, I gotta build that charge into the name. So vanadium 5 ion. All right, and I know we're all experts at Roman numerals because it's just the most useful skill that we learned back in elementary school. But let's just real quick do a little cheat sheet of Roman numerals. So 1, 2, and 3 just uses those I's. Then it gets kind of weird around 5. So 4, 5, and 6. 4 is the I before the V. 5 is just the V. 6 is the I after the V. And then let's do 7. 7's pretty much the largest charge you're ever going to see on a transition metal. All right, so here's our cheat sheet here for the charge and how we build it into the name. Right, so again, we said that vanadium with the +5 was vanadium 5 ion. Okay. In your homework system, you will use uppercase I's and uppercase V's as your Roman numerals. Okay. So now we got to move on to our anion names. Okay. So for all of our anions, fortunately, we know the charge just by looking at the periodic table, so we don't have to worry about building the charge into the name, no Roman numerals. All right? But as we saw with that example that we did, it wasn't sodium chlorine, it was sodium chloride. All right? So we stick this IDE ending on the end of the element name. All right, and this might be a little bit of a pain in the butt at first, but fortunately, as you can tell just by looking at the periodic table, there's far fewer nonmetals than there are metals. So you see the same ones kind of over and over and over again. All right, so let's just do some practice here. Let's first figure out what the charge, I'm going to get rid of my cheat sheet column labeling here. All right, let's first figure out, tell me what the charge of the following ions would be. F, O, and N based on where they live on the periodic table. All right, so fluorine lives in this column here, so -1. Oxygen lives in this column here, so -2. Nitrogen's 1 over, so -3. Okay, so fluorine, we're going to change out that ending of the name. This becomes fluoride. If you've ever heard of fluoride in your drinking water that's good for your teeth, it's this guy right here. Okay, one big mistake that I always see with fluorine, so let's just make a note. It is not fluorine or fluoride, it's fluoride, the U before the O. All right, just super common spelling mistake for that element. And again, these are all on our periodic table, right? So it shouldn't be a guessing game, but this is just one spelling mistake I see over and over again. All right, so oxygen, when it forms an ion, it becomes oxide. And nitrogen, when it becomes an element, becomes an ion, becomes nitride. All right, so again, for our cations, we don't do anything to the name of the element, it's just the element name. But for our anions, we stick this IDE ending onto the name here. All right, so that's how we name individual ions. But now we're going to put them together here. We're going to form what are called ionic compounds. right? A compound, by definition, consists of more than one type of element. And compounds are the interesting bit in chemistry here. All right, we're going to take these different elements and put them together to make these compounds. An ionic compound is going to consist of those elements in their ion form. All right. We got to have one positively charged ion and one negatively charged, at least one positively charged and at least one negatively charged to form our ionic compound here, right? So we can very easily tell, given a compound formula, whether or not we're talking about an ionic compound, because these will necessarily consist of metals, which form those cations, and nonmetals. All right, we'll graduate to a new type of compound next class, covalent compounds. But if we're looking at a formula here, how do we spy that it's an ionic compound? One of those elements is a metal. One of them lives on the left-hand side of the periodic table. The other one's a nonmetal. The other one lives on the right-hand side of the periodic table. Okay? So when we're naming our ionic compounds, all right, so for example, name the compound between the potassium ion and the chloride ion. All we're going to do is take the cation name plus the anion name and drop the word ion. So this guy right here, based on where it lived on the periodic table, it was a type 1. So I called this just simply a potassium ion. My anion, Cl-1, I had to take that element name, chlorine, but put on that IDE ending to make it the chloride ion. When I put these two together and I make a compound, all we're going to do is take that cation name, potassium, plus the anion name, chloride, and we're just going to drop the word ion when we put them together. All right, so when these two form a compound, they would form potassium chloride. All right, and the formula for potassium chloride is KCl, but we haven't gotten there yet. We'll talk about how we make these formulas here in a second. We're just going to name these compounds first. Okay? All right, so let's see if we can put it all together here. We'll do it on our periodic table so we have this to look at. All right, I'm going to give you two ions, and you're going to tell me the name of the compound that forms when we stick these two ions together. So magnesium ion and fluorine's ion. right, so if we were to put these together, name the ionic compound that these would form. Yep. So everybody take a second to do it. We'll go through it together. All right, so this is the magnesium ions. So magnesium, drop the word ion. Fluorine forms an anion, so I got to put the IDE ending on. So magnesium fluoride. All right, rubidium, positively charged ion, Rb. So first again, hunting it on the periodic table may be a bit of a challenge now. Hunt it down on the periodic table. This is rubidium. Drop the word ion. And then we have oxygen, our anion, so we got to put that IDE ending on, rubidium oxide. Okay, so we're just going to throw these two names together. All right, let's do a slightly more complicated example. Everybody try to do this one on your own here. Cu. All right, so I said these were a little bit more tricky. Why are these ones more tricky? What are we going to need to include in our name that we didn't have to worry about before? Those Roman numerals, the charge of those ions. Because just by looking at the periodic table, I can't tell what type of an ion copper forms. So when I name my compound, I have to build that into the name. Cu is one of these type 2 elements. So it's not just copper, but this is copper 2. That's the name of that ion. Right? For the type 2 metals, we got to put in those Roman numerals. So this isn't just copper nitride, but copper 2 nitride. All right, and just make note, because it might be kind of hard to see how I'm writing it here. There's no space between the metal name and the Roman numerals. Truthfully, you'll see it kind of both ways, but especially nowadays because of the internet and it makes it way easier to search for particular compounds, they got rid of the space. Okay. Likewise, over here, nickel is not a type 1, but a type 2 metal. So we're going to make this, and I always get my EL mixed up here. Nickel 2. All right, and sulfur, we haven't done this specific example yet. Sulfur becomes sulfide. Again, that IDE ending. All right, so this is, broadly speaking, the big difference between the type 1 and the type 2 is whether or not you need the Roman numerals in the name. All right, type 1, you don't need the Roman numerals. We already know the charge by you just saying sodium. type 2, you say iron, I got no clue what you're talking about. You got to tell me specifically which iron ion you're talking about. That's the logic, right? The whole sort of logic of nomenclature in chemistry is to uniquely point to one compound. We don't want any ambiguity. All right, so next step now is these formulas. All right, so let's sort of start off with a few easy examples, and then we'll make sure that we can see how we're getting these. All right, so if I'm going to make a compound with sodium ions and chloride ions, these will come together as NaCl. All right, but if I'm going to now use, instead of a sodium ion, a magnesium ion, the formula for this compound would be MgCl2. There's this little 2. It's a subscript down at the bottom, teeny baby 2. All right, what this subscript down there is telling me is that there are 2 chlorides for every 1 magnesium ion. Okay, so when we made a compound with sodium, I only needed one chloride ion. When I made a compound with the magnesium ion, all of a sudden I needed 2. Can anybody see why that may be? To balance the charges, absolutely, right? Because my magnesium ion had a charge of +2. I need 2 chloride ions to balance that charge, all right? So when we make our ionic compound formulas, the name of the game is that the net charge has to be 0. Meaning you need exactly as much positive charge as you had negative charge in order for that to be a legit ionic compound. Okay? The other thing to just note about these formulas, we don't bother to include these subscripts when it's a 1, right? I don't say Na1Cl1 or Mg1Cl2. We drop it if it's a 1. We got to include it if it's anything other than 1, all right? But we'll just leave it out altogether if it's 1. It's implied there's only one of them, all right? So let's do another one real quick. Tell me what the compound would be if we put potassium and nitride together. What would be the formula for this ionic compound here? All right, how many potassiums am I going to need to counterbalance that nitride? 3, so this would be K3N. And based on what we learned previously, what would be the name of this compound? Potassium nitride. Okay, so this is the name of the game here today. Taking these ions, putting them together, creating these chemical formulas, and naming these chemical formulas, right? Naming these compounds. Okay, so for this particular example, it may have been easy to see, but what about if we have a little bit more complicated numbers? So for example, if we took our aluminum ion and mixed it with an oxygen ion, right, what would be our formula here? Okay, so this would be Al2O3. Okay, so before we move on here, I'm going to show you a little trick about how I got this. But before we move on, just convince yourselves that indeed I have as much positive charge as negative charge here. 2 aluminums would give me a total amount of positive charge of +6. 3 oxides would give me a total amount of charge of -6, right? So I got an equal amount of positive and negative charge in this compound. That's the name of the game. That's how we're putting these formulas together. All right. We have a little bit of a trick though. Given these charges, we can play what we call the swappy swap game, where this number, this charge on my cation is going to move down here. Whoop. And this charge on my anion is going to move down here. All right, so I'm going to take those numbers and swap them when I put my formula together. That's a guaranteed way to make sure that they cancel out correctly. Okay, now just to be clear, when I put them in my formula here, they no longer correspond to a charge. They correspond to the number of aluminum ions and the number of oxygen ions. This is just a trick that helps us get that formula. Okay? What's up?
How come for the other one you didn't put N1?
Because we don't put a 1. We will leave off a 1. So this, if it's a 1, it's just implied. So you don't put it there. Yep. It's just because we're lazy and we try to limit the amount of writing that we do. All right, so then let's do one more here. Well, so actually, first of all, let's name this one because this one's also a little tricky to name. What would be the name of this compound here based on what we know about aluminum? Is it aluminum 3 oxide or just aluminum oxide? So be careful. Aluminum is one of these special 3 that we consider to be type 1, meaning we don't put the Roman numerals in the name. All right, we got these 3 exceptions for our type 1 metals. Aluminum is one of those exceptions. So this is just aluminum oxide. Unlike iron, aluminum can only form one type of ion. All right, so now for this next one, you're going to put the formula together and you're going to name this one for me. I'll put it on our periodic table screen so we can see it a little bit more easily. Try to zoom in as much as I can here. All right, so Mn is manganese. The chemistry gods were kind of cruel on this one. Notice that element 25 is manganese and element 12 is magnesium. They have very similar sounding names but are distinct elements, all right? So just be careful. This one is manganese. And what am I going to have to include in the name here? I got to have that Roman numeral. Manganese 5 sulfide. When I do my formula and I do my little swappy swap method, this becomes Mn2S5. All right, so that's how we get our name and our formula for that compound. Cool. All right, and we'll pick up with this next class. No. No, I'm going to cover acids when we get to acids and bases. I'll do acid nomenclature then.
And this Friday and next Monday will include the conversion.
Unit conversions?
Moles.
Moles. So moles they'll learn about on Friday of next week.
Also not in exam one.
No, not an exam one. Nope. We're going to stop at naming, naming covalent compounds is the last step. Right? We'll practice going back and forth between the formula and the name.
Okay.
And the polyatomic ions.
Polyatomic.
Okay.
So, the
4 of them.
ATE and the
So we're going to talk about the ITEs,
Yeah.
but the 4 that they have to have memorized are the 4 ATEs.
oh, okay, yeah.
Carbonate, nitrate, carbonate, sulfate, phosphate.
Okay.
Those are the big 4.
Okay, yeah.
No. All your constants information will be provided on the exam. Yep.
I wanted to ask about one of the examples. So you talk about magnesium chloride. Right?
Mhm.
I feel like I'm thinking something else, but wouldn't it be magnesium dichloride?
Okay, I understand where you're going. For ionic compounds, we don't use the di, the tri.
Okay.
We'll talk about that when we get to covalent compounds. So
And
for
that's when you
example,
use the prefixes.
and that's when we use the prefixes. So like carbon dioxide, both carbon and oxygen are nonmetals. We name those types of compounds different from when it's a metal and a nonmetal. So there will be no prefixes in our ionic compounding.
Okay, thank you.
Yep.
Figured out why you work so hard.
Why?
Because you want some of these bad boy overalls.
I mean, that's my goal.
That's what it is, right? It's an everyday battle, just to have a pair of overalls.
I mean, I could update my wardrobe for sure.